Hello one and all, welcome to another online video by Einstein Academy. In the last video, we looked at learning outcomes F, G, and H from the topic of atomic structure from the JCH2 chemistry syllabus. In this video, we'll be looking at 3 past year A-level questions that specifically test on these 3 learning outcomes. These are the learning outcomes F, G, and H for the topic of atomic structure. I'm not going to read through them, but instead, because the previous lecture was a very long one, I would just like to do a brief recap on the important points that we learned that students need to know very essentially to be able to solve all questions from this chapter. So we'll start with a brief recap of these learning outcomes. So we learned that the previous model, whereby the nucleus is in the middle, and then electrons orbit in a circular orbit around the nucleus. This is not the right model because it violates the Heisenberg uncertainty principle. Instead, we learned that we actually have to solve an equation. And when we solve an equation, we will arrive at atomic orbitals, which basically describe the distribution of electrons around any nucleus. So we also learned that we have the S type of orbital, whereby it looks like a sphere. And we learn, and there's only one sphere for one S subshell. And for the p orbital, it looks like a dumbbell shape. But for the dumbbell shape, the p subshell, it comes in a set of 3, whereby each one of them point along different axes. One along the z-axis, one along the x-axis, and one that's along the y-axis. Okay, so the shape of the p orbitals is in the form of a dumbbell, and there are 3 p orbitals that form one set of p subshells, and each one of them point along different axes, along the x, along the y, and along the z axis. Finally, we have the d atomic orbitals, and they look in the form of a cloverleaf, and they also come in a set of 5 d orbitals, form one d subshell, and they are in the shape of a cloverleaf pattern. Depending on the axis that they lie in between, they'll be given different notations. If they lie in between the x and y axis, it will be labeled as the dxy orbital. If they lie in between the x and z axis, then it will be labeled as the dxz orbital. If it lies, on the other hand, in between the y and z axis, then it will be denoted as the dyz axis. Sorry, dyz orbital. Students are very expected to be able to know how to draw the shapes of these orbitals, as is clearly stated in the learning outcomes. The 4th d orbital is the one whereby the orbitals lie directly along the x and y axis. It's still in the form of a cloverleaf pattern along the x and y axis, and the notation for this is dx squared minus y squared orbitals. The final orbital, it's in the form of a dumbbell shape with a donut ring in the middle. And this one has to lie particularly along the z-axis. And the notation for this orbital is the dz squared orbital. So this one, there is 3 p orbitals that form one p subshell. This one, there's only one s orbital. And this one, there is a set of 5 d orbitals that form the d subshell. Okay, so these are the shapes of the atomic orbitals, and students are expected to be able to know how to draw these atomic orbitals. The next thing that we learn is that the atomic orbitals have different relative energies, and we need to be able to deduce the relative energies before we are able to put electrons into the orbitals correctly. we learned that there's such a thing as called the principal quantum number, which is basically the energy level. The lower the energy level, the lower the energy of the atomic orbitals. And we can get the relative energies of the orbitals by reading it off correctly from the periodic table. And the way we read it is from top to bottom and left to right. So from top to bottom, this is principal quantum number 1, and this is the S block. This is the P block, and this is the D block. Okay, so from n equals to 1, we first have the 1s orbital here, and then when we go from top to bottom, when n is equals to 2, principal number, quantum number 2, this will be the 2s orbital, and then from left to right, this will then be 2p. So 2p is the next highest energy atomic orbital. Then we will go to n equals to 3, 3s. So 3s is the next highest energy orbital, followed by 3p, followed by 4s, followed by the D block orbitals. So I would like to mention again, although we are in the 4th row and it's D, but the first set of D orbitals actually occur when the principal quantum number is 3. And hence, the next highest energy orbital is 3D in this block and not 4D. And finally, we have the next highest energy orbital, which is 4P, which is basically what is required until for A-level students to know until. So you need to be able to arrange the relative energies from 1s all the way to 4p. So if we were to write up in this way, whereby this axis is the energy level, we have the 1s orbital at the bottom, then followed by the 2s, followed by the 3p, but remember, so followed by the 2p, but remember the p orbitals come in a set of 3, each one pointing along different axes. Then the 3s orbital, then the 3p, then the 4s before the 3d, as we have discussed previously in the previous slide, and the set of d orbitals come in a set of 5. 4 of them are clover leaf pattern, pointing either in between the axes or directly along the x and y axis, and the remaining one being a donut shape, being a dumbbell shape with a donut in the middle, pointing along the z-axis, the dz squared orbital. And finally, the 4s orbital. And these are the relative energies of the orbitals that you need to know for the purpose of the A-level syllabus. Now, let's say we have to fill in electrons. We will fill in the first electron to the lowest energy level based on the above building principle. You always put electrons in the lowest energy orbital first. And then if you were to put an electron into the same orbital, you have to place it such that it's of the opposite spin so that you do not violate Pauli exclusion principle. Then you fill in the next electron to the 2s orbital, then the next electron. Now we'll fill in the next electron in the 2p orbital. And now if we would like to fill in one more electron, we have the option of either placing it in this orbital or we can place it in this orbital. But Hans rule tells us that we would like to put the electrons into separate orbitals with the same spin because it minimizes repulsion and will be able to arrive at the lowest energy state of the electronic configuration. So I would just like to mention also the lowest energy configuration, lowest energy electronic configuration is also known as the ground state. Okay, if you were to place the electrons in a manner that is not according to these rules, you will arrive at an electronic configuration that is higher in energy than the ground state, and that would be called the excited states. Okay, so like if I were to put in another electron, I will put it into this orbital. And then the next electron, I have no choice but to pair it up, pair it up, pair it up. Next one, next one. So I'm just filling up electrons if I have to do so for a varying number of electrons. And this is the order in which the electrons will be placed in the atomic orbitals. And notice that when I reach this stage, by right, the electronic configuration should be 4s2,3d4. But due to the mentioning for the transition metals, there are two anomalies. And one of them is that if I were to promote an electron from the 4s orbital into the 3D orbital in this manner, I would arrive at a set of half-filled 3D orbitals, which is said to be particularly stable. And as such, the chromium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d4, instead of it being 4s2, 3d5. So this is the electronic configuration, ground state electronic configuration for chromium. And I'd just like to remind you this notation. 1s2 basically means that there are 2 electrons in the 1s orbital. And for 2p6, it means that there are 6 electrons in the 2p orbital. Moving on, fill in the next electron, the next electron, the next electron, and next electron. Now, when we reach this stage, we will arrive at the second anomaly for the transition metals. Oh, I'm sorry. Sorry, let me move backwards because I had forgotten to place the next electron. So when I reach this stage, the next electron will actually be filled into the 4s atomic orbital. And then the next one, the next one, next one, and next one. When we reach this electronic configuration, we arrive at the next anomaly. And this is basically copper. And we will choose to promote an electron from the 4s orbital to the 3d orbital, thereby arriving at a set of fully filled 3d orbitals, which is said again to be particularly stable. So the electronic configuration of copper is this manner, 4s1, 3d10, instead of the expected 4s2, 3d9. The next electron for zinc would finally go into the 4s orbital. And finally, if we have 2 more electrons, we will put it into the 4s and then the 4s in this manner. So hopefully this recap has allowed you to understand how to deduce the relative energy of the orbitals, how to fill in the electrons based on the relative energies, and also how to draw the shapes of the atomic orbitals. Now we will go ahead and look at 3 past year A-level questions, which particularly test on these 3 learning outcomes. November 2008, paper 1, question 5. Which particle would, on losing an electron, have a half-filled set of p orbitals? Now, in order to deduce which particle would indeed, on losing an electron, have a half-filled set of p orbitals, we first have to write out the electronic configuration of all these particles before we can decide. So for C-, we have the 1s2, 2s2, and 2p2. This would be the carbon atom. And since it's the C- ion, it will have 1 more electron than the carbon atom. And therefore the C- will be 1s2, 2s2, and 2p3. However, it says that on losing an electron, if the C- were to lose an electron, it would arrive at the carbon atom. And for the carbon atom, this is 1s2, this is 2s2, and for 2p2, it will only have 2 electrons in the set of p orbitals, and it will not have a half-filled set of p orbitals. It's not half-filled. For nitrogen, 1s2, 2s2, 2p4, sorry, 2p3, because it has 5 electrons in the valence shell. When the N atom loses an electron, it will form the N positive charge ion, whereby the electronic configuration is 1s2, 2s2, 2p2, which is the same as that of C-. Again, it doesn't have a half-filled set of p orbitals. N- on the other hand, will be 1s2, 2s2, 2p4. And if this was to lose an electron, it would arrive at the electronic configuration for nitrogen, and we have already deduced it to be 1s2, 2s2, 2p3. And this electronic configuration is, basically you can view of it as like that. And it is indeed true that the p orbitals is half-filled. So this would be the correct answer. Just for completeness sake, for the O+, we will start with the oxygen atom, which is 1s2, 2s2, 2p4. The O+, on the other hand, we have to remove an electron, and we'll remove it from the highest energy orbital, which is from the p orbital, and hence the O+ will be 2p3. If the O+ ion were to lose an electron, it would form the O2+ ion, and the O2+ ion would have an electronic configuration of 1s2, 2s2, 2p2. And this is not a half-filled set of p orbitals. So just a reminder again, for this type of questions, you always have to write out the electronic configuration before you can decide whether the statement is true or not. November 2012, paper 1, question 3. Which one of the following does not contain either an unpaired s electron or an unpaired p electron? So for chromium, I'm just going to use this notation to write the electronic configuration of argon because we're not really interested in the inner field D electrons. The inner field electrons are definitely paired because they are all fully filled. After this, we will have the 4s1, 3d5, and if you were to write it like this, it would be like this and like this. Okay, so indeed it does contain an unpaired s electron, and hence chromium does contain an unpaired s electron, although it does not contain an unpaired p electron. Germanium, unfortunately, I do not know where this is in the periodic table, so we have to go and look at it. So germanium is here. Okay, if we were to write the electronic configuration, it would be 4p2. Argon, 4s2, 3d10, 4p2. And for the s orbital, it would be fully filled. This will also be fully filled. But for the p orbital, it will be like that. And it is indeed true that it contains an unpaired p electron, although it does not contain any unpaired s electron. Just for clarity's sake, this one electron in an orbital is an unpaired electron, whereas if the two electrons are in the same orbital, this is a paired electron. Okay, for S minus, again, we have to go back to the periodic table to see where it is. So here, so 3s2, 3p4. One S2, 2s2, 2p6, 3s2, 3p4. And this will have 2 electrons, and here it has 1, 2, 3, 4. And it is true that it contains an unpaired p electron, although it does not contain any unpaired s electron. Finally, for scandium, it's here. So it's 4s2, 3d1. The electronic configuration is argon, 4s2, 3d1. If I were to write out the full electronic configuration for argon, I will be getting at 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And notice that it only has an unpaired d electron. However, all the electrons in the s orbital and the p orbital are paired. And hence, it is indeed true that the scandium atom does not contain either an unpaired s electron or an unpaired p electron. And this is the answer. The last question, which arrangement of the 4 electrons of highest energy corresponds to the ground state of an element in group 4? So as I mentioned before, for the ground state, it means that we have to fill up the electrons based off what we have studied previously. So the 1s orbital is right at the bottom, then the 2s, and then finally the 2p, the 3s, and then the 3p. Now, if we have a ground state of an element in group 4, it will mean that there's 4 electrons in the valence shell. So if I were to put this 1, 2, 3, 4, this would be the electronic configuration of the ground state of an element in group 4, and the arrangement of the 4 electrons of highest energy would be 2s2, 2p2, and B would be the correct answer. Now imagine if I would want to go to an excited state. An excited state is basically an electronic configuration that is not in the ground state. So for example, if I were to promote an electron from the 2s orbital in the 2p orbital, hence, okay, so sorry, let me say it for completeness sake, this is the ground state electronic configuration. if I were to promote an electron from the 2s orbital to the 2p orbital, I would get an electronic configuration of 1s2, 2s1, 2p3, and this will be considered as an excited state. There are infinite number of possibilities of excited states because we are able to promote electrons from the lowest energy orbital to the different types of orbitals. So for example, if I choose not to promote the electron from the 2s orbital, but I choose to promote an electron from the 1s orbital into the 3p orbital, this will also give me an electronic configuration that is of an excited state. So this 1s1, 2s2, 2p2, and 3p1, this would also be an excited state. Okay, so just to remind you again, when I promote electrons from the ground state, from a lowest energy orbital to a higher energy orbital, I would always arrive at an excited state. And there are infinite number of possibilities of excited states because I'm free to promote it to whatever higher energy orbital that I would like to. So this sums up the questions that addresses these three learning outcomes. Describe the number and relative energies of the s, p, and d orbitals for the principal quantum numbers 1, 2, and 3, and also the 4s and 4p orbitals. Describe the shapes of the s, p, and d orbitals. And finally, to be able to state the electronic configuration of atoms and ions given the proton number and charge. Hopefully in this video, you have learned how to apply the knowledge that we have learned in the previous lecture to solving corresponding questions. And if you have any questions, do drop it in the comments and I'll be able to answer them. If you like this video, just hit the like and subscribe button. And I'll see you for another video as we talk about the final few learning outcomes for the topic of atomic structure from the JCH2 chemistry syllabus. Stay tuned and see you again.